Hey guys, it's Greg. Today we're going to use the Keras tuner to do an automatic hyperparameter search to find the best parameters for a neural network model in TensorFlow. Yes, that's a lot of words, but seriously, it's not that bad. I'll explain everything in this tutorial. I'm doing this in Google Colab. You're very welcome to use your own computer's GPU and resources if you want to. Now, if you do use Colab, I'd highly recommend going to runtime and change runtime type to a GPU. Otherwise, it is going to take probably an infinite amount of time. Since we're using TensorFlow, unsurprisingly, we'll start with import TensorFlow as TF, let that run, and then we're going to have to do a pip install, just the one, pip install -q-u. You can probably skip that, but Keras-tuner. Make sure you get this library in pip, and then that should be all that Colab is missing. If you're getting other errors about TensorFlow, you need to do a little more pip install on your own computer. Now we're going to use a simple dataset. We'll get xtrain and ytrain and xtest and ytest. I'm hoping that you kind of know what these things mean and why I'd call it that. I'm not going to explain all of that machine learning lingo in this video. I have lots of others if you want. This is equal to tf.keras.datasets.mnist. So we're just going to use the mnist dataset, and we'll do a .load data to download and grab that. And then I can just grab all of this stuff and then add .shape to it so we can output all of their different shapes. They're all NumPy arrays, so we do that, shape and shape. We should run that. You'll see a little bit of downloading stuff here, and we see we have 60,000 training images, which are of shape 28 by 28. We have 60,000 labels, and for the test stuff, we have the same thing, but 10,000 test images and 10,000 test labels. Now, because we're not going to do anything too complicated, we're just going to immediately do a pre-processing by dividing everything by 255. So xtrain is equal to xtrain over 255.0. That is very standard for any image-like data. We're just normalizing the data. And xtest is equal to xtest over 255.0. So that hopefully xtrain.min and xtrain.max are respectively 0 and 1, and they're in decimals. Now here comes the real meat of this tutorial. And this part is going to be a little bit confusing because we're going to be using, or making a function that relies on a variable that is of a class that we don't really know yet. But just trust me, stick with this, and it's really not so bad. If we define model builder, which is going to return a TensorFlow Keras model, specifically a sequential model, this takes one parameter, which we're just going to call HP for hyperparameters. Don't worry about the class of this object. It's honestly not important. Model is equal to tf.keras.sequential. So we're going to start by making a sequential model, and then we will add, well, actually you could add whatever you want here, but we're just going to start by flattening the model and also at the same time doing an input. So we'll do model.add tf.keras.layers.flatten, and we will specify that the input shape is what? Well, it takes 28 by 28 images. That's what they were before, so we'll put that there. Now we'll make a variable called HP_activation. And what this hopefully makes you think of is hyperparameter activation. What is the best activation function that we want? Well, we would make it an HP. Notice that that's the same parameter over here, HP.choice. Okay, I'm saying don't really worry about what class this thing is. It happens to have a method called choice. And whenever you want, say, a choice of discrete items, this is what you would do. We will call this one in particular, you probably guessed it, activation. That's just a name we're setting here. This is the activation function that we're going to try and figure out what is best. What different options do we have, or what different choices do we have? What could be best? Well, we're just going to tell it, hey, actually, we want ReLU and TANH. Try to figure out which is the better one, ReLU or TANH. Here we're going to use an integer value for, say, hey, for the first layer of our network, how many different nodes do we want? Well, you and I, we would try, say, 32, 64, 128, 512, something like that. Or maybe you would look at a research paper. But here we're going to do HP underscore layer 1. So this is basically how many nodes is going to be in layer 1. Well, this is going to be an HP.int. Okay, so an integer, and we're going to call it layer 1. And we set a min value. We'll say, well, we don't want less than 1, so we're going to do 1. A max value, this is however big you want, really, although it's going to be very complex, computationally complex if you choose a massive value. Max value is equal to 1,000. And then so we don't specify just like, so that we don't blow up the computational complexity here, we're going to set a step equal to 100. And hopefully that looks the same type of, if you've used Python's range function, you'd set a beginning, an end, and a step. It's really the same thing there. Now what we're going to do is just copy this same thing, because we're actually going to make a neural network where we have, first we flatten it, and then we're going to do one layer. It'll figure out the number of nodes and the activation function for that. And then it'll do another layer, which again, we'll choose a different number of nodes, but it'll have the same activation function. So to do that, we would actually just copy this in. Yes, I will utilize the GPU soon enough. So we'll do HP layer 2, and this is going to be layer 2, and we'll specify that it's still min value 1 and min max value 1,000 and step 100, all the same thing. But the reason I'm doing this again, a new instantiation, is because I don't want to say that these two layers have to have the same number of nodes. You could do that. We want to say that the first layer is going to have some number of nodes in this range, some number of nodes in this range for the second layer, and then they're both going to have the same activation function. How do we actually do that? Because we haven't specified the model yet. It's really, really easy, and it might be exactly what you expect, or at least it's really what you hope. Model.add tf.keras.layers.dense, because you add a layer. How many units do you want? Usually you specify a number. Here we're going to specify the HP underscore layer underscore 1, because that's that choice of integer there. We would also do the activation, which has got to be activation equals HP underscore activation. Okay, so here instead of choosing numbers, we are choosing our HP dot either choice or integer, different values that we hope it'll try to figure out what is the best ones. Now that specifies the first layer after the flatten. If we wanted a second layer, well, we still haven't defined that yet. We would make another one. So that's a copy paste of exactly the same thing, but units is going to be up to layer 2 to try and figure out. So since we have layer 1 versus layer 2, they are going to be different values to figure out. Maybe it'll think the same value, I don't know. And since we're using both of these are going to be HP activation, it'll be all of them are going to be ReLU or all of them are going to be tanh. And now you have to make the neural network make sense still. And so what makes sense? We do a model.add tf.keras.layers.dense with how many different outputs are there. This is the MNIST problem, so it's going to be 0 through 9 on a softmax. So 10 of these on an activation is equal to a softmax. And then you do your model.compile. We're going to do that in this function as well, because we're returning a compiled model in this function. Model.compile with an optimizer is equal to what? We're just going to choose the Atom optimizer. tf.keras.optimizers.atom with a learning rate. Hey, what if we don't know the learning rate that we want? Maybe we could find it automatically. Okay, so here we could also do a choice. Since we did a choice on the activation function, ReLU or tanh, we could easily do an HP learning rate is equal to an HP dot choice, where we'll name it, guess what, the learning rate, sounds good. And the values, well, what are a typical set of values? Really, it's this list right here, which I'm just going to copy in. It is all of those different decimal values that Andrew Ng would probably tell you to try. We could also do to the -1 as well, although that's probably too big. And so it's going to be one of these values is probably the best one. Okay, so down here we do learning rate is equal to HP underscore learning underscore rate. This loss is going to be tf.keras.losses.sparse. It's sparse because of the way we have the labels set up. It's not one hot encoded, it's just the number, and so it's sparse. Categorical cross entropy, that's what we want to maximize or minimize. And then the metrics is equal to Accuracy is fine, but you could plug in your favorite metrics, of course. Return the model. Okay, so we're making this function, which has this thing we don't really understand, but it doesn't matter. This thing that we're passing in has these two options. You can do choice and int, at least that's what we're using. And so you go to build your model, however things you expect to do or whatever you want to do for sure, you would do those as usual. But if you ever have an option where you want to say, choose a set of values, like what do I think is best? Well, I'm going to do an hp.choice and make that a variable. And if you want stuff like a bunch of different values in a range, well, we'll do an hp.int and set a min value, a max value, and a step. We did that for 2 layers, and we did for the learning rate, we did a choice. Which one of these do we think is best? And then how do we add those into the model? Keras completely supports you just putting in that variable there. So instead of that being a fixed number for when you're adding that dense layer or whatever layer, convolution layer, whatever you want it to be, this works for CNNs as well. You would just put in this number here, or put in this parameter as if it were a number. And as long as it makes sense with what you're doing here, then it should work okay. So activation is up to the function to figure out. Units, HP layer 1, layer 2, it's going to figure out the best learning rate. And there we go. That's all we set. You could, of course, do other things. As I said, with CNNs or RNNs, you could do whatever you wanted, of course. But we are just going to run that. And unsurprisingly, I have some sort of a syntax error. I will put another bracket there, another bracket there, hp.choice as well. And there we go. Okay, sorry about those errors. Now, this is the other thing that we really haven't seen before. We haven't used it yet. Up here, you saw that we defined this kerastuner thing. And we have to import this. Okay, we have to do an import kerastuner as KD. So right here, sorry, KT, KD. Import kerastuner as KT. And this is where we can actually use kind of force it to use this function here for building a model down below. So after we import this thing, we can make a variable called tuner, which is equal to a kt.hyperband. Okay, you can look up the algorithm online if you want to really understand this, but don't look too much into the details here if you don't really care about figuring out exactly how to optimize every single thing here. It's really not a big deal. We're just going to add some parameters. So we'll pass this function, most importantly, first the model builder function. So it's got to return, this function has got to have this hyperparameter variable here and add those in wherever you want them. And it's got to return a compiled model. It does that, so we're good to go. What objective do we want? As usual, objective is some sort of function of the validation, some loss function. We'll just do validation is accuracy. So I guess the opposite of a loss function. But what do we want to maximize? We'll try to maximize the validation accuracy. As you know, maybe accuracy is not the best metric possible, but that's usually a fine choice. We will set a max number of epochs for each model to be 10. So it's going to train a bunch of models and do some algorithm where it trains many, many different models. How long do we want to train each model for? We specify that here with max epochs is 10. There's this thing, a function of a parameter of the algorithm, which is called the factor, and we'll set that equal to 3 as per the TensorFlow blogs. And then here, there's just 2 here for setting up directories. We'll set directory equal to something called dir to make it easy. And then within that directory, it'll make something called a project. And this is also just a directory name or a subdirectory name. Project name equals X. Okay, so we set up our tuner there, and that's really it for the complex stuff. It's not too bad from there. You may have heard of something called early stopping, and so we're going to do that. You don't have to do that, but it's probably a good idea, especially because we're training so many models. So we'll do stop early is equal to a TensorFlow callback. Stop early is equal to df.keras.callbacks.early stopping. And then we're going to monitor the validation loss. So val loss is the monitor. And set a patience equal to 3, which says that if the validation loss does not improve on 3 consecutive epochs, we're going to stop early because it doesn't look like it's getting any better. Maybe it might, but it doesn't look like it is. And then we do this thing called tuner.search, which is extremely analogous to model.fit, but we have a tuner. And so we're tuner.searching, not model.fitting. Tuner.search with xtrain and ytrain. A number of epochs, which we're going to set to 50, which is a pretty big number, but there you go. Validation split is equal to 0.2 is relatively common. You could do another number, of course. And callbacks is stop early. Okay. Notice that we are doing the validation split within this, and at the top here, we're doing train and test, and so this will be left for testing. We're actually not going to use it here, although I hope that you probably know how to test a model. Otherwise, I have some videos for that. Yeah, so we'll do the validation in here. We'll just let that go. And this is the one that will take an extremely long time. So I'm going to run this. No, it won't. And sorry, apparently I missed an equal sign there. So callbacks is the list of stop early, and let that run. So basically what you see here is in this column, it's what it's trying currently. And so it's going through some epochs over here. Don't worry too much about the training details. It's not super important. But here it's trying TANH. It's trying 901 for the first layer. It's trying 501 for the second layer. It's trying a learning rate of 0.0001. And boom, it's already trying something else. Of course, the best value so far is whatever it just had, because that was the first thing that it tried. But now it's trying ReLU. And notice that ReLU only showed up once. Actually, now it went back to TANH. It seems to prefer TANH is better. So here, it's trying all of the different options here. There's some stuff that we didn't really see, but this is part of the algorithm itself, the brackets and the rounds. And I'm just gonna talk to you after this runs. Okay, for me that took about 10 minutes on here. It might be shorter or longer for you. Of course, if you didn't want it to take that long, then feel free to change those values. Maybe make the step size bigger, make the min and max size values closer to each other. There's a lot of different things you could easily do to make it run faster. Now, what can we do? So we have a model. We did tuner.search. Actually, we don't have a model. We have hyperparameters. We know which ones are best. And we can get these ones with best hyperparameters is equal to the tuner dot, well, get best hyperparameters. And then numTrials is equal to 1 and sub 0. Don't worry about that. I know it's a little bit weird. We are getting our variable best hyperparameters from our tuner search there. Now what we actually need to do is build our model from scratch now. We'll do model is equal to tuner.hypermodel.build, and you just need to pass it this time best hyperparameters. We don't really need to worry about all of that other stuff about what the model looks like. We've already defined in general what it looks like, and here we just build it with the best hyperparameters. And as with before, you can always do a get history as equal to model.fit this time with same thing really, xtrain, ytrain. Epochs, just pick a big number, it should be fine. We're going to do is stop early. If you wanted, you could actually do an extra level here to try and look at the best number of epochs from if you were to train this twice, basically. But we don't have to do that. Epochs equals 50, validation split equals 0.2. And as with before, we're going to set our callbacks equal to early stopping, or stop early is what we called it, so that it doesn't run for a super long period of time. If we run that, it should not take too long since we trained several models earlier. We're really just training one now. If it completed the earlier step, it most definitely can complete this step as well. And it turns out that it stopped at 10, which basically means that it found the best one at like 7 or 8 or so. The validation accuracy slowly went up until we got a 97.85. And if you wanted, we could check our history.history, which is that dictionary that is really just a pandas data frame. You could look at this as a pandas data frame. If we were to do import pandas as PD, and we did pd.dataframe with that history.history, then you would see that all of our results from training that most recent model are stored in this history. And yeah, there you have it. That's your model, and you have your model. You could do whatever you wanted that with that variable there. You could save it and you could use it right now if you wanted to. It's if you don't know how to save a model, it's really easy. Just look up how to do a Keras model save. It would store it to a file over here, and easy peasy. So I hope that was helpful. If you wanted to do this for a CNN or an RNN, you would just do exactly what we had before. If you wanted to change the number or allow a flexible number of convolutions in a filter or filters, then you could do an integer for a range there, or you could possibly do a choice for a couple different values, and you could do the same thing for any of those really parameters there. Like for the window size, for the pooling, you could specify the windows, of course. And yeah, that would, of course, you could do it for an LSTM, like how many different nodes you wanted in that as well. I hope this was helpful, and yeah, I'll see you later, guys.